Okay, we'll get going today. For once, we don't have any announcements before class, but as always, if there's anything you want me to announce, please let me know. So we're going to continue on today talking about electron configurations. So what we ended with last time, if you can remember what happened 5 days ago, what you'll remember is that we talked about quantum numbers for electrons, which is a series of mostly integer values that define different things about the orbital and then the electron itself. So the first three quantum numbers, n, L, and m sub L, we use to define an orbital, both which relates to the size and energy of the orbital, it relates to the shape of the orbital, also to the orientation of that orbital as we started drawing pictures of and all that. And then at the very end we close with the idea that there's a fourth quantum number, m sub s, which has values of plus or minus 1/2, that is a property of the electron itself. So there's four quantum numbers that are needed to define any electron in an atom. And so what we're going to start doing is talking in more detail about that, and if we have multiple electrons in the atoms, what are the quantum numbers that they have. And before we do that, we need to define what's called the Pauli exclusion principle. Another very angry scientist who came up with something very important. And the definition of Pauli exclusion is that no two electrons in an atom can have the same quantum numbers. I shouldn't use a highlighter to write, I should use a pen, that works better. So no two electrons in an atom can have the same set of quantum numbers. Okay, so when you have a multi-electron atom, each electron in that atom is going to have a unique set of quantum numbers associated with it. Now there's some important implications of this. If we recall, the value of that fourth quantum number only had two allowed values. And so what this means is that if the first three quantum numbers define the orbital that the electron is in, the fourth quantum number can only have two values, plus 1/2, minus 1/2. They can't be the same, and so that means there's a maximum of 2 electrons per orbital. So if you're going to put 2 electrons into the same orbital, you can have one that has m sub s plus 1/2, one that has m sub s minus 1/2, but you cannot have more than 2 electrons in a single orbital. And then in a situation when an orbital does have 2 electrons, as we'll see later today, you don't always have 2 electrons in an orbital, but you can have at most 2 electrons in an orbital, and when they do, there's something important about that fourth quantum number as well. That means the spins are what we call paired. They have to be opposite. It's kind of weird terminology, paired spins meaning that they're opposite in direction. But that's the chemical terminology we use. And that means when you have 2 electrons in an orbital, one is going to be spin up, or plus 1/2 for that m sub s value. And then the second electron has to be the opposite of that to satisfy the Pauli exclusion principle. Okay? So that's sort of the implications of the Pauli exclusion principle when it comes to counting out the maximum number of electrons that can go in an orbital. It just ends up being 2. And so that allows us to then talk about some other relationships related to that. So if we're told, if we're given a certain shell number, value of n, and we want to say, what's the maximum number of electrons that can go into the first shell, or the second shell, or the third shell, or so on, one thing we learned last time is that for a given shell number, the number of orbitals that are present is n squared. So in the first shell you have 1 orbital, in the second shell you have 4, 9, 16, and so on as you go up in values of n. But then if we know now that the Pauli exclusion principle tells us there's a maximum of 2 electrons per orbital, remember these are maximum values that we're talking about here, that means the number of electrons that are present in a given shell is going to be just 2 times n squared. Okay? So the first shell would have a maximum of 2 electrons, the second shell would be 2 times 2 squared, which is 8. The third shell would be 2 times 3 squared, which is 18. So the higher the shell number, the more electrons you could potentially put into that shell because there are more orbitals available. And then the other thing is we talk about the maximum number of orbitals in a subshell. So a subshell is defined by 2 quantum numbers n and l together. And the number of orbitals in that subshell is only determined by the value of L, 2L plus 1, which then tells us that the number of electrons in a given subshell is just going to be 2 times that, 2 times 2L plus 1. Or if you prefer simpler notation, is 4L plus 2. So if we know the value of L for a given subshell, we can calculate the maximum number of electrons that can go into that subshell. So let's just do a couple of random examples. So if we're in the third shell, which means n equals 3, remember that the shell number is that first quantum number n, the number of electrons present, the maximum number of electrons present in the third shell is just 2n squared, which is 2 times 3 squared, or 18. So if we have some number of electrons in a multi-electron atom, the most that can go into the third shell is going to be 18. Okay? And then if we're just talking about the 3s subshell, let's talk about the different subshells that are in the third shell. So if n equals 3, we have 3 values of L, 0, 1, and 2. And so there's 3 subshells in the third shell. There's always n subshells in a given value, for a given value of n. So if we have the 3s subshell, the number of electrons maximum in the 3s is given by 2 times 2L plus 1. That's the value for a subshell. So it's going to be 2 times 0 plus 1. So for an s subshell, the value of L is 0, which means we can put 2 electrons into the 3s subshell. For 3p, 2 times 1 plus 1, so L is 1 for the p subshell. That means you can put 6 electrons into 3p. And then for 3d, 2 times 2 plus 1, so L equals 2 for the d subshell. It means 10 of the electrons can go into the 3d. So when you have the third shell, maximum number of electrons is 18. Out of those 18 electrons, 2 of them go into 3s, 6 of them go into 3p, 10 goes into 3d, the sum of those still being 18. So this is telling us the maximum number of electrons we can put into each shell and subshell, but what we're going to be focusing on today is determining how many electrons go into each subshell and how do we fill up those subshells with electrons when we have multi-electron atoms, and so the order that they get filled in, how many each one has, the quantum numbers of each of them, all that stuff we're going to touch on today. So what we need to talk about then are the factors that influence the energy of the electron in an orbital. So when we're placing electrons into orbitals, there are 2 things that contribute to the energy of that electron. So one thing we've already been familiar with from talking about the Bohr model is the idea that protons and electrons are attracted to each other. That's a very simple chemical principle. And so as you add more protons to the nucleus, so when we're talking about multi-electron atoms, each time you add another electron, you add another proton to the nucleus, of course, if we're talking about neutral atoms. And so if you go to larger atoms that have more protons in the nucleus, you're going to have stronger attractions between the electron and the nucleus. So the strength of that attraction between an electron and the nucleus depends on how many protons are in the nucleus to be attracted to that electron. And this results in a lower or more negative energy value. Okay? So the more protons you put into the nucleus, the stronger the attraction, the lower the energy of the electron is going to be. And this we can see from the Bohr equation. Remember that in the Bohr equation, even though I don't know if your book even talks about this, we don't really deal with it in the homework problems this week, in the Bohr equation you have that z squared term, which says that the energy levels are also a function of how many protons are in the nucleus. So the more protons you put in the nucleus, the lower the energy of the electron is going to be, or the more negative of a value it's going to have. So that's one factor that contributes to electron energy. But as we start talking about multi-electron atoms, we also have, as the name implies, more than one electron present. So you're going to have electron-electron repulsions as well. You're not just going to have attractions between the electrons in the nucleus. You're going to have the electrons repelling each other as they sort of surround that nucleus. So in these multi-electron atoms, anything with more than one electron, these electrons are going to experience repulsive interactions with other electrons. Okay, so you experience these repulsive interactions with other electrons, and these are destabilizing, meaning they increase the energy. Just going to get this to stop lagging. Oh, it's being flaky already. It's too early for this. Alright, so we have these two factors that contribute to the energy of an electron in a multi-electron atom. Now the idea is that, and this is going to be something that comes up time and time again in chemistry, things want to have the least amount of energy possible. They want to be, and that's what we call the most stable situations, when they have the least amount of energy possible. So the electrons are going to arrange themselves in an atom. When you have more than one electron present, they need to arrange themselves to maximize the proton-electron attractions. So on one hand, they want to be as close to the nucleus as possible to maximize those stabilizing interactions, but at the same time, they need to minimize the electron-electron repulsion. So it's kind of a combination between, or a competition between these two things going on at once, and the electron wants to get to the minimum energy value possible that comes from a sum of those two interactions. So it's kind of, that's the idea of what electrons want to be able to do. And so then the two factors about orbitals that affect this proton-electron attraction and the as well as the interaction of the electron-electron repulsion. The two factors that affect that related to orbitals are called shielding and penetration. So shielding is the idea that we know that the value of n determines the size of the orbital. So the larger the value of n, on average, the electron is going to be farther away from the nucleus. So if you have electrons that are close to the nucleus inside of that orbital, then you're going to have some of that charge of the nucleus is going to be shielded or partially canceled out. And so this is the idea where you reduce the nuclear charge experienced by an electron. When you have this effect called shielding. So when you have inner electrons that are closer to the nucleus in a lower shell value, in a lower shell number, these inner electrons are going to partially block the outer electrons from the nucleus. And it's going to stop them from feeling that maximum nuclear charge. All right, and so we call this the effective nuclear charge, or Z effective, and it's going to be less than the total nuclear charge for the outer electrons. Now, sometimes it's helpful to draw a very simplified picture of this. I'm going to try to sketch one real quick. This is overly simplified because it's not considering differences in the shapes of the orbitals and all that stuff. Well, let's say you have a nucleus that has 4 protons, so it has a 4+ charge. So let's say that's your nucleus. And then you're going to have, let's say you have 2 electrons at let's say the n equals 1 shell that are going to be close to that nucleus. And then your other 2 electrons are farther away in the n equals 2. The idea of shielding is that the 2 electrons that are closest to the nucleus, these 2 here, are going to more or less experience that 4 plus charge in full. They're going to be close enough to the nucleus, they're not blocked out by any other electrons. So to them it seems like there's 4 protons that they're attracted to, and they're very happy because of that, because they want to maximize that attraction. But then these 2 electrons that are in a higher n value and are farther away from the nucleus, they're going to be blocked by the 2 electrons that are closer, and so to an approximation, the effective charge that these outer 2 electrons experience is only 2 plus, because the 2 minus charge from the electrons that are inside of them sort of cancels out part of that nuclear charge 4 plus. Now it doesn't quite work that simply, but you can sort of hopefully see the idea that the electrons that are closer to the nucleus are going to block some of the outer electrons from experiencing that full charge. And so the point being that if you want to maximize the proton-electron attractions, you need to get closer to the nucleus. So those are the ones that tend to have lower energy, or the ones that are closer. But then let's say we have 2 orbitals or 2 subshells that have the same value of n. So so which one of these is going to have a lower energy? Now, as I've told you, if we're comparing, let's say 2s and 2p, 2s is going to be lower energy. Let's see why that is. So this effect is called penetration. Get your giggles out now. So the idea here is that if we have 2s and 2p, we're drawing again the radial probability density here, that 4 pi r squared psi squared term that we talked about last time, the probability of finding an electron at some distance from the nucleus. So because 2s is going to have 1 radial node, it's going to have sort of this shape here that we talked about last time. And then the 2p is going to have a different radial probability density. It's going to it's not going to have a node, so it's going to be just a simple peak like that. The most probable radius is similar, but it's actually a little bit smaller for 2p, as it turns out. So you get something like this. But the idea here is that the 2s electrons are better able to penetrate close to the nucleus because they have this little region of high probability very close to the nucleus. So penetration is the ability of an electron to get close to the nucleus. It's lagging again. This program is having trouble too. Alright, so penetration is the ability of an orbital or an electron in that orbital to get close to the nucleus. And what this does is it reduces the effect of shielding. Because there's some probability of the electron being found close to the nucleus, it's not going to be shielded as effectively by the inner electrons, because they can sort of sneak in there and get close to the nucleus and experience that positive charge that it wants to experience. I should label these a little better. This one's the blue one is 2s. And the red one here is 2p. Color code those. Alright, so that's 2s and 2p. And then the trend sort of follows for the values of L. So the energy of the 2s orbital is going to be less than that of 2p because of the ability of the 2s electrons to get close to the nucleus. And what that means then for all subshells, if you're comparing the energy of the subshells within a given shell, so you're going to have the S subshell is going to be lowest in energy because it's the one that's best able to penetrate close to the nucleus, and then the P, and then the D, and then the F. So within a given shell, the ordering of the energies of the subshells is just an increasing order of L. So the S is going to be the lowest energy subshell for that, then the P, then the D, then the F. So that's fairly easy to understand, but the problem is that you sometimes have overlap between subshells. We're going to talk about that later. So in other words, they're not always going to be in order in terms of the value of n as well. So there's some, as the one we'll see earliest on is that 4s is lower in energy than 3d. So even though 4 is larger than 3, the 4s, because of the better penetrating ability of the s electrons, is lower in energy. So we need to understand the full ranking of subshells, which we'll come to in a little bit. Now, the next thing I want to talk about that's important for understanding the relative energies of orbitals is the idea of degenerate orbitals. So these are not orbitals that have difficulty following the law. What degenerate means in the context of chemistry is that they have the same energy. So there are going to be some orbitals in an atom that have exactly the same energy. And which ones are degenerate, it's fairly easy to tell. So if you have all the orbitals in a given subshell are going to be degenerate. And we kind of already talked about this last time. When you have a multi-electron atom, the energy of the orbital is determined only by the values of n and l. It's not determined by the third quantum number m sub l or by m sub s either. So any orbital in a given subshell with the same n value, the same l value, all those orbitals are going to have the same energy or be degenerate with each other. Alright, so as an example, if we look at the 2p subshell, we saw last time when we drew the pictures of these that there are 3 individual 2p orbitals, the reason being that there are 3 values of m sub l. So 2l plus 1 gives us 3 possible orbitals or 3 possible m sub l values. So in the 2p subshell there are 3 orbitals. We saw that they were 2px, 2py, 2pz. Their only difference was their orientation in space, nothing else about them. So all 3 of these orbitals have exactly the same energy in, well, any atom, and specifically in multi-electron atoms. So these 3 orbitals are going to have the quantum numbers 2, 1, minus 1, 2, 1, 0, and 2, 1, 1. And all 3 of those orbitals are going to have the exact same energy because the energy is only determined by the first 2 quantum numbers, n and l. So all the 2p orbitals have the same energy. If you go to higher subshells like 3d, there's going to be 5 orbitals there, and all 5 of those will all have the same energy as each other. So when you have subshells, you're going to have orbitals within those subshells that are all degenerate with each other. And so then what we're going to start doing now is what's called the Aufbau principle. So now that we sort of know some of the factors that influence the energy of orbitals, we're going to start basically ranking the orbitals from lowest energy to highest energy. And when we fill those with electrons, we're going to fill the lowest energy ones first and then just keep adding electrons until we run out of electrons. So we fill the electrons from lowest to highest. So the Aufbau principle is referred to as the building up principle. And not surprisingly, this is a German word, Aufbau. And what it tells us is that electrons are added one at a time to the lowest available subshell that's available. So the lowest energy subshell that's available. Okay, so it's going to be this building up principle where we add electrons one at a time, and the next electron always goes into the subshell that's lowest in energy that still has some empty space in it. Okay, we have to remember Pauli's exclusion principle, which tells us that it's going to dictate the maximum number of electrons that go into a subshell, but if there's available space in that subshell, we're going to add the electrons there first, whatever's lowest energy and still available. And then once we see examples of this, this will make more sense. Okay, so that's the lowest energy sublevel, and that gives us what's called the ground state configuration. So we know from the Bohr model that ground state means the lowest energy state. And I may have told a corny joke about that at some point. But then the ground state configuration for a multi-electron atom, it means the same thing. It's the lowest energy arrangement of all the electrons in that atom, which comes by putting them into the lowest available subshells possible. Okay, so the ground state configuration is the arrangement of electrons into sublevels. So we're partitioning the electrons into different sublevels. Depending on how many electrons there are, we're going to have different numbers of sublevels that are filled or partially filled. And we want to find the arrangement that has the lowest possible energy. And the way we do this is by filling the lowest energy subshells first and then just adding electrons until we have filled up all the available spots, or however many electrons we need. So the way that we write these configurations is that we're going to write out each sublevel that has electrons in it. And it's going to have sort of this general form here. Each sublevel is going to be written with its N and L values with a superscript, where the superscript is the number of electrons that are in that subshell or sublevel. N is the first quantum number, as is always defined. Or the shell number. And then L is going to be one of the letter designations for the second quantum number, S, P, D, or F. So just like we conventionally do for a subshell, we call it either the 1S or the 2P. We use the letter abbreviation for the second part of that. Okay, so each sublevel is going to be written out in this form where we list the subshell and then we tell us with a superscript X how many electrons are in that subshell. We write out as many subshells as we need to add all the electrons into it. So that's kind of what we talk about for Aufbau principle. Now, if we're talking about Aufbau, we need to remember what order the subshells come in, because we're going to fill the lowest energy one first, and then the next one, and then the next one, and so on. Now, there are these diagrams, I think your book probably has it, these where you list all the subshells sort of in a diagonal fashion and draw these diagonal lines through them, and it tells you what order they come in. That's all well and good, but we're not going to give that to you on the test. So the way that you want to learn how to do this is with the periodic table. So if you have the periodic table in front of you, you don't need to memorize the order of the sublevels, and you will always have the periodic table available on tests. So don't even bother trying to memorize the order that these subshells are filled in, because the periodic table has that information built into it. It's sort of why the periodic table is shaped the way it is. Okay, so let's look at how we can use the periodic table to know the order of subshells. So the elements are arranged in order of atomic number, and also as you go through the elements in sequence in order of increasing atomic number, that tells you which subshells come next in the series. And so how that works is that each part of the periodic table is labeled as a certain subshell. Okay, so what we do is for the value of N, which is that first quantum number, that's coming from which row of the periodic table we're in. So the first row represents N equals 1, and then 2, 3, 4, 5, 6, and 7. Okay? So the value of N tells you what row of the periodic table you're in. And then we have certain groups of columns that are what we call the blocks of the periodic table. So these first two columns of the periodic table here, which I'll highlight in blue, this is the NS block. So as we're progressing through these columns of the periodic table, we're adding S electrons. And so the first one would be the 1s, and then 2s, and then 3s. Now there's one that's left out here, sort of in a weird place in the periodic table. So helium is also part of the NS block of the periodic table, even though it's really located in the P block. So the way this works then is if we wanted to add electrons to hydrogen, hydrogen is in the 1s part of the periodic table. It's in row 1, it's in the S column. So the electron for hydrogen goes into a 1s subshell, or the configuration for hydrogen is 1s1. If we wanted to add a second electron, we come over to helium. We have to remember that that's also 1s, so helium would be 1s2. Then for the third electron, we go to lithium, and that's the second row, so that's going to be 2s. And then that electron goes there, and then this is 2s2, and so on. So we go through the elements in order and know which blocks. So that's the S block, we have more to do still. These last 6 columns over here, excepting the, I can't draw brackets. This is terrible. These last 6 columns here, which excluding helium, so it's a little hard to draw. This is going to be the NP block. So as we go through this part of the periodic table, we're adding electrons to P subshells. We'll get a bunch of examples later that will illustrate that. Okay, and then so that's going to include, as I said, all 6 of these columns are what we call the P block, excluding helium, which is still part of the S block, even though it's in a weird spot. All right, now the two blocks of the periodic table that are a little bit more confusing, but still nothing too difficult for us. This middle part here is the D block, but it's not going to be ND, it's going to be N minus 1D. And so what that means is that the D block starts in the fourth row of the periodic table, but it's N minus 1D, so these first D elements, we're going to be adding 3D electrons, not 4D. It'll be 4 minus 1D or 5 minus 1D. So this is 3D, 4D, and 5D as we go on. They don't correspond directly to the row of the periodic table there. We have to remember that for the D block. All right, so if we highlight the D block of the periodic table, it's going to be these 10 columns here, my favorite 10 columns of the periodic table, if you were wondering. And then a bunch of, this one only goes up to 109. I think we've gotten all the way to 118. So there's a lot more elements that aren't even on here, but we're not going to deal with those. And then finally the last one, down here at the bottom, sort of separated out from the rest. What we should recognize for this is that these are the N-2 F blocks. Now we have to realize where these come from. So they're sort of snipped out of the periodic table. You notice that it starts with atomic number 58, and so that comes out of the sixth row of the periodic table, because here's 57, and then we jump down here to 58. The only reason we do that is to make sure that the periodic table is a reasonable aspect ratio. If we put these F blocks where they're supposed to be, it would basically make these fifth and sixth rows of the periodic, the sixth and seventh rows of the periodic table would be like super wide. And it would just look terrible and awkward, and couldn't even project it on the board with any reasonable clarity. So it just makes things clearer to read. But realize that where those come from is from that sixth and seventh row, and these are the N-2 F. So the first F block is the 4F, 6 minus 2, so this is 4F. The second is 5F. We're not going to deal a lot with F elements, but it will come up from time to time when we're filling electron configurations out for other elements, so we have to be aware of that. And so these two rows with 14 elements in each are the F block of the periodic table, and they're sort of snipped out from rows 6 and 7 up above. And so that's sort of how we label the periodic table in terms of electron configurations. And so when we're adding electrons to orbitals, we go through in order through the periodic table, and we add the electrons to the next subshell that we come to as we progress through the periodic table in numerical order. And we'll get a bunch of examples for that in a second. Now the last thing we need to talk about before dealing with electron configurations in more detail is one other rule for adding electrons, which is called Hund's rule. Okay? And this deals with what happens when we fill degenerate orbitals. Now Hund's rule is not really important if we're just trying to determine the subshell configuration. So Hund's rule, if we just want to know how many electrons are in the 3s or the 2p subshell, whatever subshell, we don't really need to consider this if we just want to know the total number of electrons. But if we want to know how the electrons arrange themselves into individual orbitals within those subshells, and if we want to know whether those electrons are spin up or spin down, we need to understand what Hund's rule is as well. So that's going to be something that is sort of a second level consideration when we're doing electron configurations. So this deals with what happens when degenerate orbitals are filled. We first put one electron into each orbital. And as we fill each orbital with a single electron, all of those electrons that we add in individually are going to have the same spin. We do this before pairing two electrons into the same orbital within that subshell. And basically what you're trying to do here is maximize the number of unpaired electrons. Okay? So there are sort of two reasons why this is. We don't need to get into too much detail for the reasons, but I'm sure some of you at least are curious about why this is. So the first thing is, Hund's rule minimizes electron-electron repulsions. So if we think about it, let's go to the 2p subshell. We have three 2p orbitals, px, py, and pz, all pointed in different directions in space. If we put one electron into each of those orbitals, that's going to keep them farther apart from each other than if we try to put two electrons into the same orbital. So you want the electrons to get as far apart from each other as possible to minimize electron-electron repulsions. And Hund's rule allows you to do that. So you spread the electrons into different orbitals before you start pairing them up in the same orbital. That keeps the electrons farther away from each other and minimizes how much they repel each other. Now the other part of Hund's rule is a little bit more quantum mechanical, and the idea of why do the spins have to be the same. That's because there's another component to the energy in the Schrödinger equation, which is called exchange energy. And so when you have electrons with the same spin, that's sort of a stabilizing or beneficial arrangement of those electrons. And so that's something we don't have to worry about, but that's kind of why the spin matters as well. The important thing is we just have to know what Hund's rule is and how to use it, more so than the reasons for why it occurs. Now the other thing to think about is when does it matter? It really only matters for the three subshells that have degenerate orbitals. So F subshells only have one orbital in them, so you don't have to worry about degeneracy. But if we're filling electrons into a P, D, or F subshell, we have to make sure we keep Hund's rule in mind. And it really only matters if they're partially filled. If we're completely filling up a subshell, if we're putting the maximum number of electrons into it, all of the electrons are going to be paired and all of the orbitals are going to be doubly filled. So it doesn't really matter if we think about Hund's rule for those situations. But if you're doing a partially filled subshell, you have to keep Hund's rule in mind to know which individual orbitals have electrons in them and what's the relative spin of those electrons. And we'll see examples of that here in a minute. And I already said that, so I don't need to write that again. Okay, so that's Hund's rule. Let's just go through now and start doing examples of electron configurations so we can understand how to use the periodic table to do this and how to write these out. So let's start with a slightly more interesting one than hydrogen or helium. Let's start with boron, which is Z equals 5. And so when we want to add electrons into boron, we have to go through the subshells in increasing order of energy and add the electrons until they're filled. Okay, so let's go back to the periodic table that we drew earlier. Okay, so boron is here. So we want to figure out where the electrons go in boron. There's going to be 5 total. So we start at atomic number 1. We have 1s1, 1s2. There are 2 electrons that are in the 1s. Then we go to this one. This is row 2, 2s1, 2s2. There are 2 elements in the 2s columns. That means there's going to be 2 electrons that can go in there. And then finally we come to boron. This is also in the second row, but it's in the p block now, so it's going to be 2p, and this is the first element, so it'll be 2p1. So 1s1, 1s2, 2s2, and then 2p1. Okay, so we fill them in order. Sorry, didn't do that. So this is the configuration for boron. First 2 electrons go into 1s. Second 2 electrons go into 2s, and then that 5th electron goes into the 2p, which is the part of the periodic table where boron is. Okay, so that's how we would write the configuration. Now some additional details about this come from filling the actual orbitals. So the 1s subshell has 1 orbital. We have 2 electrons to put in there, so they have to be arranged like that. So the up arrow means spin up, the down arrow means spin down. And when you have 2 electrons in a 1s orbital, they have to go in that way to satisfy Pauli exclusion. For the 2s, you also have 2 electrons, so it's 1 up, 1 down. And then for the 2p, we just have 1 2p electron. Now the reality of the situation is there's 6 ways we could put this electron in. We could put it in any of these 3 orbitals, and we could put it either spin up or spin down. All of those would have the exact same energy because, remember, all 3 of these orbitals are at the same energy, and spin up and spin down have the same energy. By convention, we always usually put spin up first, and we fill them left to right. But that doesn't have to be that way. So this is a valid way of writing this. You could have also put the electron in the 2nd orbital, 3rd orbital, spin up. If there's only 1 electron, it doesn't matter how you put them into these degenerate orbitals. The energy will be the same. But by convention, this is how we do it. And this would then have 1 unpaired electron. So that's often a question we'll ask you about electron configurations, how many unpaired electrons there are. So unpaired electron is one that doesn't also have an electron of the opposite spin. So these 2 are paired, 1 spin up, 1 spin down. These 2 are paired, 1 spin up, 1 spin down. But this electron, which we drew a spin up, does not have another spin down electron with it, so that's an unpaired electron is how we say it. Okay? So this would have one unpaired electron. Let's go into carbon now. The next one on the periodic table, Z equals 6. And so if we go to carbon, we're going to do things the same at first. So carbon is just 1 over here now. We have 1s1, 1s2, 2s1, 2s2. Now we go to the 2p block. It's going to be 2p1, 2p2. So we add one more electron to 2p to fill up carbon to get a total of 6 electrons. We're still in the 2p block, so the second electron still goes into the 2p subshell. Keep doing that. And this is the same document. Come on. All right. So for carbon, we have still same 5. The first 5 electrons go in the same way. Then we have one more electron that's still also going to go into the 2p subshell, so it's going to be 1s2, 2s2, 2p2. That's how the 6 electrons arrange themselves. You'll notice that these inner electrons, 1s2, 2s2, 1s2, 2s2, they don't change. So if those are filled, they're going to still be filled if we go to atoms with more electrons. They're always going to stay filled. We're never going to change the order that we fill things, but we're just going to have more electrons to put in there. So this is how carbon looks, and this is one where we actually have to use Hund's rule. So when we fill the orbitals here, we still get the 2 paired electrons in each of the 1s and 2s orbitals, but then we have 2 more electrons to put in 2p. And remember that what Hund's rule tells us is that we have to fill up individual orbitals first before we pair them up into the same orbital, and we have to keep the spins the same. So the first one, by convention we put there, as we did before, we have one more electron to put in, and by Hund's rule, it has to be in a different orbital. So it has to be in one of these last 2, and it has to be spin up. Again, there's a lot of possible ways you could do that are still all valid, but the conventional way to do it is to just put it into the next orbital that's available and still keep the same spin up. Okay, so that's the key points there. So that's Hund's rule in action here, dealing with the 2p subshell for carbon. However you decide to arrange those electrons, they have to be in 2 different orbitals and have the same spin. That's what Hund's rule tells us. Okay, so any questions on that? Relatively simple ones. So we're not going to go through these in detail, but if we went through the rest of the P block, we would have 1s2, 2s2, and then for nitrogen it would be 2p3 because it's the third. Oxygen would be 2p4 because it's the fourth in this column, in this block. Fluorine is the 5th, so it would be 2p5, and then 2p6 for neon would finish up the P block of the periodic table. So we just keep adding one more electron to the 2p orbitals until we came to the end, 2p6. Okay? Let's do a couple of slightly bigger ones now, sodium and magnesium. All right? So we'll go through the full configuration for these, but then we'll see that there's a slightly shorthand method to write it. So if we do sodium, which is Z equals 11, now we're going down to this guy here. We again have to add the electrons in numerical order going through the different blocks of the periodic table. So it's going to be 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. And then when we come to sodium, we're in the third row. So it's going to be 3 s blocks, so 3s, and this one electron that goes into 3s to take us to sodium. So the full configuration for sodium is going to be, we have a bunch of filled subshells, 1s2, 2s2, 2p6, and then that last electron, that 11th electron, as we saw, goes into the 3s subshell, so it's going to be 3s1. So that's the full configuration for sodium. Now one thing we'll notice is that we have a bunch of filled subshells, and this is only 11 electrons, but as we go to atoms that have a lot of electrons, we're going to have a lot of subshells that are filled. So very often what we do is we group all of those filled subshells together up to whatever the P6 configuration is, and we just write the element that corresponds to that. So if we go to the periodic table, 1s2, 2s2, 2p6, that filled core of electrons corresponds here to neon. That's the configuration. And then for sodium, we add one more 3s electron. So these first 10 electrons correspond to the configuration for neon, Z equals 10. And so what we'll often do then is write this as a shortcut method where we take whatever that filled configuration is at the end, and then we just write whatever's partially filled after that, 3s1 in this case. So a shorter way and a conventional way of writing the configuration for sodium would be neon 3s1. That means it has all of the electrons that neon has in those same subshells plus an additional 3s electron. So then what we call the nearest noble gas, we're going to define noble gases here in a second, but the noble gases are the elements that are in this P6 column of the periodic table, the last column of the P block. So we go to the nearest noble gas, we write that in brackets, and then we just add whatever electrons come after that as a shorthand method. So we write the nearest noble gas in brackets, which corresponds to those inner electrons, or the ones that are completely filled, the subshells that are completely filled. And we just indicate those with brackets so that we don't have to write out all of them individually. Now you should know how to do both. So when you'll do homework problems this week and when you'll do exam questions in the near future, you'll see examples of both types of configurations. Either the full configuration with all of the 1s, 2s, 2p, and so on written out, or the abbreviated configuration where we put that noble gas configuration in brackets as a way of abbreviating it. So you need to be familiar with both of those. They will both come up. Let's do one more example that's very similar. Magnesium, Z equals 12. And so if we want to do the shorthand method for magnesium, we find it in the periodic table, it's there. So the 2p6, or the noble gas that comes before magnesium, is neon still. So that's the one that comes immediately before it, the one that's closest to it, with a smaller atomic number. And so we can still just write that in brackets. Then we have to figure out what are the additional electrons beyond that. And so if we come to magnesium, we see that magnesium is also in the third row. It's in the S block, so it's going to be 3s1, 3s2. So the two additional electrons also both go into 3s subshells. So magnesium would be neon 3s2. Okay? So that's another way to write the configuration for neon. And then a concept that comes out of this is the idea of what are called valence orbitals or valence electrons. These are the outermost electrons. The only ones we're going to worry about for now are the main group elements, which are those that are in the S and P block. These are the electrons with the highest principal quantum number n. All right, we'll talk in more detail about the importance of valence electrons, but really the chemistry of an element, what kind of reactions it does, what some of its key physical and chemical properties are, a lot of that is determined by how many valence electrons it has. So those are going to be the electrons that are furthest away from the nucleus and the ones that have the highest principal quantum number if you're talking about elements that are in either the S or the P block of the periodic table. So if we go back up to magnesium, the ones with the highest principal quantum number are these 3s electrons. All the other ones have quantum numbers of 2 or 1. So there's going to be 2 valence electrons for magnesium. Sodium would have 1 valence electron. It's just that last 3s electron is considered valence. The rest of these are what we call core electrons. So they're the electrons that occur beyond the noble gas core, and they're the ones that are most important for determining the chemistry of that element, as we'll see in more detail later. Okay, so that's a concept that comes out of the shorthand method, is recognizing which ones are the valence electrons. Now, if you have a P block element that has S and P electrons in the outer shell, all of those would be considered valence electrons. So as an example, we did carbon up here, 2s2, 2p2. There's 4 total electrons that have the highest principal quantum number of 2, so this would have 4 valence electrons. So now that we understand that concept, we should be able to determine how many valence electrons there are. So for P block elements, which these two are, it's the S and the P that occur with the highest quantum number n. So there's 2s2, 2p2, all 4 of those are labeled as valence electrons. Okay? Okay, 4 valence electrons for carbon and 3 for boron, 2s2, 2p1. Alright, so that's valence electrons. Now, the next thing I want to talk about is the electron configuration for transition metals. We don't really have to do anything differently here for the most part. The only thing to remember is that the NS subshell is filled before the N-1D. So this is the first place where we have a little bit of a discontinuity, so where we have 4s coming before 3d and 5s coming before 4d. So even though the principal quantum number is higher for 4s, it actually is lower in energy than 3d. Now that comes straight from the periodic table. So if we look at the D block of the periodic table, the first element in the D block here is scandium, and we see that you have the 4s block, which corresponds to calcium and potassium, 19 and 20. The 4s comes before the 3d. So you fill the 4s, then you start adding 3d electrons. That's one thing to keep in mind. You don't have to necessarily memorize that, but it comes from the periodic table, and don't let it weird you out that you're putting 4s electrons in before you're putting in 3d. That's normal. That's what happens in the transition elements. Okay, so that's one thing to realize. And then when we're counting valence electrons for transition metals, it's going to be all of the NS electrons. So there's going to be typically 2 of those for most transition metals, and whatever d electrons are in there as well, in that outer shell. And this is again just for that highest value of N, not for all values of N. Alright, so let's, as they say, level up and do an example of a transition metal electron configuration, a little bit more complicated than what we've seen before. So let's use osmium here, which is, we'll find on the periodic table, it's OS is the symbol. Alright, so if we go to OS, this is a pretty complicated one, it's just a good way to say a lot of these different things. Alright, right here, atomic number 76. So we want to figure out, what is the electron configuration for that one, and we're going to write it in the shorthand notation to save ourselves some time and avoid a writing cramp. There's 76 electrons now. So if we look at osmium, we find the noble gas that comes before it, or the 2p6 element that comes before it. So that's going to be xenon here, number 54. That's the last noble gas before osmium. You never go after it, you always go before it. So the core electrons we're going to abbreviate as xenon, Xe. And then we have to add the rest of the electrons in order of the subshells as we come to them, going down to osmium. So those are the core electrons. Now let's see what we have. Okay. So there's going to be 22 more electrons because xenon includes 54 electrons. We're at 76 for osmium, so you have to add 22 more electrons beyond the noble gas. So what we come to after xenon is row 6 of the periodic table. We come to the S block first. We're going to do 6s2. Then the next element here is in the N-1, so it's going to be 5d1. Remember, after this we skip down to the F block. So we go 5d1, then we go down to here to 58. We go in numerical order. So this is going to be the 4F, and it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 to get across the 4F. That takes us to atomic number 71. So that's 4F14. Then we go back up to 72, which is another 5D. So we have 1, 2, 3, 4, 5 more 5D electrons to get to osmium. So osmium is there. So it's a little bit weird because there's this discontinuity in the D block where you go from 5D1 down to 4F and then back up to D. So we could write the configuration like this, but this is not the standard way of doing it. So if we just write everything in order, we came to 6s next, and there's 2 electrons there. Then we saw that the next electron goes into 5D, but from there we jumped down to the F block and saw that there were 14 F electrons. And then we came back up to the 5D to fill the remaining 5 electrons to get to osmium. Okay, so that's what we saw. We don't really write it like this. We're going to group all of the 5D electrons together and write it like this. 6s2, 4f14, 5d6. So you don't necessarily have to think about it the way I did, because we're not going to give you elements in the F block to do. So the only time you're going to even have F electrons is for these heavier transition metal D block elements, and you're always going to fill the F block. So another way to do this is just to recognize that after we go through 6s2, we're going to come down here. We have 4f to fill, which is 14. Then for the D block, we have a total of 1, 2, 3, 4, 5, 6 D electrons to get to osmium. It's in the 6th column of the D block. Okay? So there's a little bit of confusion there because of the discontinuity, but in total, this is what we have. 6s2, 4f14, 5d6. And for all these transition metals, if there are F elements, they're going to be filled anyway, so you don't necessarily have to worry about those too much. Just recognize that they are there. And so we see there's a total of 22 electrons, 2 plus 14 plus 6, that come after the noble gas xenon configuration that represents the core electrons. And that's what we wanted. Okay, so that's the configuration. How many valence electrons we have. So as I just defined here, it's going to be all ns and n-1d. So we have 2 6s electrons, we have 6 5d electrons, so we're going to have 8 valence electrons. The 4f electrons do not count as valence electrons for transition metals, but those 8 electrons are considered valence, which means they can participate in a lot of the chemistry that this element does. So 8 valence electrons, 6s2, 5d6, a total of 8. And then finally, if we fill up the subshells and the orbitals individually, what we find is that the 6s is completely filled with 2 electrons, 4f14. So if we wanted to put those in correctly, we would go 1, 2, 3, 4, 5, 6, 7 to satisfy Hund's rule. But then we have 7 more, so those 7 get paired up. 1, 2, 3, 4, 5, 6, 7. So as I said, for a filled subshell, Hund's rule doesn't matter because they're all going to be filled, they're all going to be paired. And then finally we go to 5d6. And if we want to correctly fill the 5d6 subshell, we have to keep Hund's rule in mind for this as well. So we go 1, 2, 3, 4, 5. We fill 5 of them individually first with the same spin, and then the 6th electron gets paired up with that one, or with any of them really, but we conventionally do it left to right. So that's how we would add 6 electrons to make sure that we maximize the number of unpaired electrons, and that will give us 4 unpaired electrons for this element. Okay? So if we ask you for the number of unpaired electrons, you need to draw little diagrams like I have down here where you consider individual orbitals and make sure you include Hund's rule when you're adding them to those orbitals with the appropriate spins. Alright, the last thing we're going to talk about for electron configurations is some exceptions. Now there's only 2 exceptions we're going to expect you to know on the periodic table, where you can't just use the predicted position on the periodic table to directly tell you the electron configuration. So one of those is chromium, Cr. So if we predict the electron configuration for chromium, let's see what that comes out to. Okay, so chromium is here, we're on atomic number 24. So the noble gas that comes before chromium is argon, so we're going to have a core electrons that are represented by argon. And then beyond that we have 4s2, 1, 2 in the 4th row, and then we have 3d, this is a 3d block, 1, 2, 3, 4 to get to chromium here, atomic number 24. So it's going to be 4s2, 3d4 are the valence electrons. So that's what we would predict for chromium, but that turns out to be wrong, and this is one of the ones you just have to remember as being an exception. So we would predict argon 4s2, 3d4. But that's not quite right. The actual configuration is 4s1, 3d5. We don't change the number of electrons, we just take one of the electrons from the 4s and bump it up to the 3d, so now we have 1 electron in 4s, 5 in 3d instead of 2 and 4. Still 6 total valence electrons. And the reason for this is because of half-filled subshells being favorable, or perhaps a better way to think about it is that we want to maximize the number of unpaired electrons. The 4s and the 3d subshells, as it turns out, are really close to each other in energy. They're not that far apart. So we actually gain a lot of energy by moving one electron up and having more unpaired electrons than we would by keeping it in the lower subshell. So because 4s and 3d are really close energy levels, we can put one of the electrons up, bump it up, and we can bump it up to a higher level, and then that gives us more unpaired electrons. We have 6 unpaired electrons instead of 4, which is a more beneficial situation. Okay, so those half-filled subshells are favorable, and this is one exception to the normal electron configuration that we want you to know. And then the other one is copper, Cu. So if we predict the configuration for copper, argon is still the nearest noble gas, but then if we go to this one, we're at towards the end of the 3D block over here, atomic number 29. And so we do 4s2 once again, and then we do 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Copper is the 9th element in the 3D block. So what we would predict the configuration for copper to be is argon, then we have 4s2, 3d9. So this is also not correct. We again take one electron from the 4s and bump it up to 3d. So it's 4s1, 3d10 instead, because the filled d subshell is favorable. Not as intuitive why in this case, because you still have the same number of unpaired electrons. Both of these configurations would only have one unpaired electron, but it's still slightly favorable to bump this up and get this filled 3d10 configuration. So that's what we do for copper. These are the only two exceptions you have to know. For any other element that we ask you about, just use the periodic table, fill the subshells in order, and don't worry about any of this weirdness. Now there are many more exceptions than this, especially in the heavier elements down in the 6s, 6th and 7th row of the periodic table. There's a lot of weird configurations that don't quite match the periodic table, but these are the only two we want you to know about as being exceptions. Okay? So then what we're going to come to now is an overview of the periodic table. So we now know how to determine electron configurations, and the importance of doing that. Yes? Yes. For the copper one? Maybe. I mean, it's always those factors that are important. I don't know which factor is most important for copper though, because the 4s electrons are able to penetrate close to the nucleus, but then the 3d electrons I think are not shielded as much, so there's like two effects, and it's hard to know which one's more important for that. But yeah, it's all going to be related to those effects we talked about. It's just not always easy to predict or rationalize why. So the importance of doing electron configurations is that the electron configuration of an element, especially for the valence electrons, determines a lot about its property. And so because of that, elements that are arranged in the same columns of the periodic table, which have the same valence electron configurations, relatively speaking, are going to have very similar properties. And so we group them together and label them in certain ways. Okay, so let's see how we do that. So at a basic level, we have two types of elements. We have nonmetals and metals. I mean, of course, right? So if you have nonmetals, you also have metals. And the dividing line between these is over here in the P block. So let's see if I can get a good highlighter for that. So I'm going to highlight this dividing line. So in general, elements that are on the left of the periodic table are metals. Elements that are on the right are nonmetals. And where's the exact dividing point? It's sort of the staircase here that starts at boron, and you just zigzag your way down. Alright, so I drew this sort of yellow highlighted staircase here. It's not shown on your periodic table. You want to know about where that is. Elements to the left of that line are classified as metals. Elements to the right are classified as nonmetals. So, and then ones that are on the borderline we have a sort of a special category for called metalloids. We'll talk about those at the end. Okay, but anyway, the ones that are nonmetals are the ones on the right. So these ones are all nonmetals. Those are nonmetals. Those three, those two, and carbon. Make sure I didn't forget any. So those are your nonmetals. They're on the extreme right of the periodic table. They're separated from that dividing line there, and those are what we call nonmetals. Now within the metals, we have two different categories. I guess three different categories of metals. Three. So the first one are called main group metals. All right, we used the term main group earlier, and it refers to any element that's in the S or the P block of the periodic table. And so the main group metals are going to be the ones on the left. It's going to be these ones here. And then also the metals that are in the P block, which includes the rest of this column, and then some of the bottom ones here. These are all considered main group metals. So they're to the left of the staircase, but they're either in the S block of the periodic table or the P block. Those are what we call main group. Maybe going in a weird order here, but the next one we'll talk about are called the metalloids. So the remaining ones in the P block that I haven't highlighted yet are called metalloids. So that's going to be these ones that are right on the borderline: boron, silicon, germanium, arsenic, antimony, and tellurium. So 1, 2, 3, 4, 5, 6 that we classify as metalloids. This is one that's, depending on which textbook you read, you might see slightly different classifications. For example, some people consider antimony to be a metal, some people consider it to be a metalloid, some people put silicon as a non-metal, some people as a metalloid. There's different classifications, there's not a real clear divide there. But the ones that are on the staircase, those 6 elements that are on the staircase are conventionally classified as metalloids. They're in between metals and non-metals, as we say. And then the other 2 types of metals that we have, before I get to that, I forgot one thing, which is we have one more non-metal over here. So hydrogen, even though it's on the left side of the periodic table, is still a non-metal. Okay, so it's another one that has sort of a weird position. You have to remember that hydrogen is a non-metal, even though it's in that leftmost column. And then finally, the other 2 categories of metals are going to be, how many colors do I have here? I'm running out of colors. We haven't done red yet. All right, we have the transition metals. Oops, don't use that. All right, so transition metals are one other category of metals. And these ones are in the D block of the periodic table. So these 10 columns here with these 3 or so rows, 3 to 4 rows, those are all considered transition metals. So they're metals, they're on the left side, but they're in the middle of the periodic table. They're called transition metals. And then finally, the last one, one more unique color here. These ones down here, the F block, we call the inner transition metals. Alright, so that's going to be these 2 columns here, these 2 rows here, 14 elements in each. So we call inner transition metals. So that's kind of the basic categories we give. And then certain columns of the periodic table also have specific names associated with them. So beyond these 5 characterizations, metals, non-metals, main group metals, all those, some of the columns have special names as well. So this first column of the periodic table is called the alkali metals. All of those except for hydrogen. Hydrogen, as we said, is a non-metal. But lithium, sodium, potassium, rubidium, cesium, and francium are all alkali metals. So that first column of the periodic table, excluding hydrogen, are alkali. This one here are the alkaline earths. So similar name, but it's the second column instead of the first. We call them alkaline earth metals. So that would be beryllium, magnesium, calcium, strontium, barium, and radium. So that column, that whole column there is considered alkaline earth metals. The second to last column, which is in the non-metal series, we call halogens. So these are some other terms you're going to want to know. So fluorine, chlorine, bromine, iodine, and astatine are considered halogens. And then finally, as we kind of already talked about, this last column of the periodic table, this P6 column, are called the noble gases. All right, and they're noble not because they pertain to royalty, but because they're noble, meaning unreactive. They don't react with many things, so they're very inert is another way to say it. Inert gases is sometimes used, but it's all of those: helium, neon, argon, krypton, xenon, radon. Those are the noble gases. Okay. So this is kind of an overview of the periodic table, how we divide elements into different categories depending on where they are. And now there's some other properties that are also going to be related to the position on the periodic table. So we want to learn how some of the key properties of atoms and elements depend on where they are on the periodic table. So that's one of the important points about the periodic table, is the understanding that the electron configuration, which is related to the location on the periodic table, dictates some of the important properties. The first one we're going to talk about is atomic radius. Now, a very simplified picture of atomic radius is just how big is the atom. Okay. Now, there's a more precise definition than that. So if we had a metallic element, the atoms are all very close to each other, as we'll learn later on in the course. So you have all these atoms that are very close to each other. You can measure the position of the nucleus very accurately. And so basically for a metal, the atomic radius is given by the distance between two nuclei in a sample of that metal, which we can measure using certain experimental techniques. So that's what we mean by atomic radius. It's, I guess, half of that distance is the radius. So it's 1/2 the distance between adjacent nuclei. Okay. Now we know that, another simple way to think about it is how big the electron cloud is. We know that the electron cloud doesn't have a definitive starting and end point. It's all probabilistic stuff for quantum mechanical models. But if you think about how much space the electrons occupy, that's sort of a simple way to think about atomic radius. Now, if we do nonmetals, it's a little bit different because we don't have discrete solid arrangements of atoms, but we can still look at, for example, two nonmetals bonded to each other. And so we can measure, in this case, again, a distance between the two nuclei. So this distance is 199 picometers for chlorine, 10 to the minus 2. So if we have two chlorine atoms bonded to each other, they're going to be separated. The nuclei are going to be separated by a distance of 199 times 10 to the minus 12 meters, picometers. And so that means the radius of a chlorine atom is going to be half of that distance. Or about 100. So for diatomic elements, where we have two of the same atom bonded to each other, we can again measure the distance between them and say the radius is half of that. And then if we wanted to do another element, let's say carbon, we can measure the distance between carbon and chlorine in a compound. We would find that it's 177, and that distance is then going to be the sum of the radius of chlorine plus the radius of carbon. We already know the radius of chlorine is 100 from measuring chlorine by itself, and so we get the radius for carbon is 77 picometers. Now the point is that not that you need to memorize these numbers, but to recognize that the way we measure atomic radius is by just measuring distances in a bunch of different types of elements and compounds, and then usually the values you see reported are sort of average values. So you're not going to get the exact same number when you measure it in different systems, but you're going to get close to the same number and you average those together. And the point for this course is to know, based on the position on the periodic table, is the radius of the atom going to be bigger or smaller compared to another one. Okay? So that's what we want to talk about for atomic radius. And so the general trend for atomic radius is that if we go down a group, so that means we go from top to bottom on the periodic table. So remember, groups are the columns, periods are the other rows. The principal quantum number increases as we go down. We talked about that earlier today. And so we can think about this logically then. If the principal quantum number is getting bigger, are the electrons going to be closer to or farther away from the nucleus? Farther away. Remember, the value of n tells you the rough size of the subshell or the shell. And so that means as you go down a column, the electrons get further and further away from the nucleus. And so as you go down, the radius increases. So we're going to draw the trends for increasing atomic radius over here. and it increases as you go top to bottom. So if you look at two elements that are right on top of each other, let's say hydrogen and lithium, lithium is below hydrogen, so lithium would be expected to be larger than hydrogen if you're comparing two that are in the same column. Now if we go across a period, left to right on the periodic table, that's the other direction we can move on the periodic table. So as we go left to right, the effective nuclear charge increases because we're adding more protons to the nucleus. And when you add more protons to the nucleus, that pulls the electrons a little bit closer to the nucleus. Okay, so you're adding more protons, you're increasing the effective nuclear charge, and so the electrons are pulled closer to the nucleus. And that means the radius then goes down as you move left to right. So the increasing trend for radius would be right to left. Right? So radius increases as you go top to bottom. It increases as you go right to left. And that's for two different reasons, really. One is that as you go top to bottom, you're adding electrons to subshells that are further and further away from the nucleus. As you go from left to right, you have fewer protons in the nucleus. You have a smaller effective nuclear charge, so the electrons are not pulled as tightly to that nucleus. So that's one trend we want to be aware of. And then the last one we're going to talk about today is ionization energy. So what is ionization energy? We have to define it first. We've talked about it in the context of the Bohr model. It's the energy required to move one electron from an atom. So in other words, as the name implies, we're trying to form an ion by removing an electron, and this is how much energy it takes to remove that electron. And this specifically refers to a gas phase atom. It's defined for atoms in the gas phase, not terribly important for us now, but that's just the precise definition. And so in general, what it looks like is you have a gas phase atom, and we're trying to figure out how much energy it takes to remove one electron. So we form a positively charged ion. We release an electron that goes off and becomes a free electron. And the change in energy for this process is equivalent to the ionization energy. And we put a little subscript of 1 because this is the first ionization energy. It's the energy for removing one electron from that, okay? So that's why the little 1 is there. And these are always positive numbers. So it always takes it always takes energy to break the attraction of the electron to the nucleus. So no matter what element you're talking about, it's a positive number for ionization energy. And there are then two factors that influence it. And again, we think about going down a group and across a period. And it's really closely related to the atomic radius arguments that we just saw. As we go down a group, the principal quantum number increases. We saw that the radius increases. And that means the attraction to the nucleus decreases or weakens. So if the electron is farther away from the nucleus, it's not held as strongly by the nucleus, so it takes less energy to rip that electron off. So as we go down a group, the ionization energy goes in the opposite direction as radius. It's going to decrease as we go down a group. And then as you go across a period, again the trend is opposite, because as we go across a period, we're adding more protons to the nucleus, so our effective nuclear charge increases, and the size, or the radius, decreases. So really for two reasons, as you go across a group, you have more protons to hold that electron, and they're closer to that nucleus because of that. So that means the attraction is stronger, and it takes more force to rip one of those electrons off. And so that attraction to the nucleus increases as we go across, which means the ionization energy also increases. Okay? So then drawing that trend on a periodic table, if we want to talk about increasing first ionization energy. Now this only applies to the first ionization energy. We need to be very clear about that. as we'll see in a little bit, there's successive ionization energies. It increases as you go up, and it increases as you go left to right. So that's what we talked about on the last slide. Now there are some places where the ionization energy doesn't follow a smooth trend. So we have to be aware of some exceptions here. So if we go to boron and aluminum, which are here and here on the periodic table, these have abnormally low ionization energies. Which means, because as we have, the configurations for these are NS2, NP1, and if we just remove one electron, we get to a very stable NS2 configuration. Alright, so because we only have one little p electron there to remove to get to a stable configuration, boron and aluminum have abnormally low ionization energies. So as you're going from left to right, you would normally expect the ionization energy to increase, but for these ones, they're actually going to be a little bit lower than the ones over here to the left of them. Okay, so that's one little blip in the trend. And then if you go to oxygen, selenium, and sulfur, oh come on, we're almost done. So if we go to oxygen, selenium, and sulfur and selenium, which is these ones in the periodic table, those are also going to be abnormally low. And that's because in this case the configuration is NS2NP4, and if we remove one electron, we get to an NS2NP3 configuration. As we said, half-filled subshells are usually pretty good, so this is also another stable configuration. So, you know, if you're going to a stable electron configuration by removing an electron, it's generally speaking easier to do that because there's a significant amount of electron-electron repulsion for that fourth p electron. So by removing it, you're able to relieve some of that. So we'll skip the last slide and do it next time, but I'll see you on Wednesday where we'll finish up Chapter 2 and move into Chapter 3.